All right, we are in section 5.3, talking about medians and altitudes of triangles. So who uses this? Sculptors who create mobiles of moving objects can use centers of gravity to balance the objects together. Let's first talk about what a median of a triangle is. The median of a triangle is a segment whose endpoints are at the vertex of a triangle and the midpoint of its opposite side. So the median, once again, is a segment that connects the corner, the vertice of one part of the triangle, to the midpoint of the opposite side. Every triangle has three medians, and the medians are concurrent, as shown in the construction below. All right, we are not going to construct this, but let me just go over what we're doing here. So we want to construct a centroid of a triangle, and I'll talk about that in a little bit. The first thing we do is we have a triangle, ABC. I want to construct the midpoints. So I did that by drawing your arcs, constructing the perpendicular bisector, because it bisects it, so that's how we get our midpoints. They then labeled the midpoints X, Y, and Z. They connected the midpoints, to the vertices of the side opposite of it. And then they labeled the point where they intersected, which is called point P. Now, once again, this is the point of concurrency. So, the point of concurrency of the medians of a triangle is called the centroid of the triangle. The centroid is always inside the triangle. Always inside. Inside. Don't forget that. Inside. The centroid is also called the center of gravity, because when we're doing real-world problems, it becomes the point where a triangular region will balance. The center of gravity is the centroid of a triangle. So, here's your centroid theorem. The centroid theorem says this: the centroid of a triangle is located always 2/3 of the distance from each vertex to the midpoint opposite side. So I'll say that again. The centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. All right, so here's what it states. Now you're going to have to just visually look at this, but it shouldn't be too bad to figure out which part of this is going to be 1/3 and which part's 2/3. So if you look at, for example, segment AY, the length of AP is going to be 2/3 the length of AY. The length of BP is going to be 2/3 the length of BZ. And the length of CP is going to be 2/3 the length of CX. So, using the centroid to find segment lengths. Let me make it a little bigger. So in our triangle ABC, we know that AF is 9 and GE is 2.4. Find each length. Now, I'm actually going to go through all of the steps to show you what would happen in a proof. This is important that you pay attention. I know you guys can look at this and say, well, Mr. Humphreys, AG is going to be 2/3 of this entire length. So if I know the entire thing is 9, why don't I just take 2/3 of that? You absolutely can't. But what happens if I put it in a proof? You don't know what to do. So here's what's going to happen. We know that AG, which is the longer piece, is going to be equal to 2/3 of AF. And the reason is AG is the longer part, so that's going to be the 2/3 part. Our reason would be the centroid theorem. By substitution, I know AF is 9. And that would give me a length of 6 for AG. Now, if I went to the next one, and this is where it gets a little tricky for students, CE. Now, most of you, if not all of you, could look at this and do this completely in your head. I want to find the length of CE. That's this entire length. And I'm going to circle it. What do I know? EC is what I have to find. We know GE is 2.4. So somebody you, actually most of you, are probably going to look at that and go, well, Mr. Humphreys, if I want to find CE, I know EG here is 2.4. That's only a third. So why can't I just take 2.4 times 3 and get 7.2? You're absolutely right. If this is not a proof, you can absolutely do that. But what would happen if I said in a proof, find it? Notice that your centroid theorem says nothing about a third. So you actually have to go the long way and start with what we know. So looking at this segment here, I know that CG will be equal to 2/3 of CE. But I have nothing to plug in. I don't know CG and I don't know CE. So then you have to know, what am I talking about? I'm talking about segments. So you have to use the segment addition postulate. So this reason here was centroid theorem. I'm going to use the segment addition postulate to say CG plus GE equals CE. That is the segment addition postulate. Now, I know CG is equal to 2/3 CE, so I'm going to plug that in. So because of substitution, I'm going to get 2/3 CE plus GE equals CE. I now am going to subtract 2/3 from both sides, 2/3 CE that is. That gives me GE equals 1/3 CE. What did I use? Subtraction property of equality. So GE is now 1/3 of CE. I know what? I know EG is 2/4, so I'm going to use substitution. So that's going to give me 2.4 equals 1/3 CE. I now multiply both sides by 3, so I use the multiplication property of equality to multiply both sides by 3. And my answer then is CE, which is 7.2. Example number 2. The diagram shows the plan for a triangular piece of mobile. Where should the sculptor attach the support so that the triangle is balanced? Well, before we said that the centroid of a triangle is representing the center of gravity. So we have to find the center of gravity that would make this balanced. So we have to find the centroid. So we know our 3 vertices of PQR. So since the centroid of the triangle is the point of intersection of the 3 medians, we need to write the equations for 2 medians and find their point of intersection. So let's pick 2 points and find the midpoint of the sides. So let's find QR. Let's find the midpoint of QR. So midpoint of QR. And 0 plus 6 is 6, divided by 2 is 3. 8 plus 4 is 12, divided by 2 is 6. So 3, 6, right here, I'm going to call that point M. That's point M. So now I'm going to do the midpoint of PR. So 3 plus 6 is 9. Half of that is 4.5. And 4 plus 0 is 4. Half of that is 2. So 4.5, 2. I'm going to call that N. So I'm going to connect these right now using blue lines. Now, if you wanted to do the other side, we can do that as well. And I'll show you what's going to happen. Midpoint of QP. So we do 0 plus 3, and half of that is 1.5. And then 8 plus 0, half of that is 4. So 1.54. And let's call that L. If I connected that, there are all 3 points meeting at our centroid. Now, it looks pretty easy. It looks like it's all meeting at 3, 4. But let's say you're thinking to yourself, uh-oh, I don't know where the point of intersection is. Well, if you don't know the point of intersection, you have a couple ways to do it. You could have written your equations. Now I'm going to enlarge this from the triangle. We know that a horizontal line here, that's going to be y equals 4, and our vertical line is x equals 3. You could just take those two values and plug them in, and that would be the point of intersection of a vertical and a horizontal line of x equals 3 and y equals 4. The point of intersection is 3, 4. You could have also found the other equation of this line, and that would be y equals negative 4/3 x plus 8. You could have then found the system of equations and solved that. You would have also gotten an answer of 3/4. All three lines intersect at the centroid, or the center of gravity, of 3, 4. So we've already talked about the median of a triangle. Now remember, the median of a triangle is what? It's when you connect the vertex of a triangle to the midpoint of the opposite side. The altitude of a triangle is a perpendicular segment from a vertex to a line containing the opposite side. But it's not a midpoint. It's just perpendicular to it. Every triangle has 3 altitudes, and altitude can be inside, outside, or on the triangle. So in this triangle, QRS, it's not the red triangle, it's this black triangle right here. QY, the altitude QY, is inside the triangle. But RX and SZ are not. Notice that the lines containing the altitudes are concurrent at P. This point of concurrency is called the orthocenter of the triangle. Also notice that the side lengths have been extended by the dotted line. Now these are not actual sides, but they're invisible. And you're probably thinking, well, why is this outside the triangle? Because it's outside the triangle because you can't connect point R and make it 90 degrees inside the triangle. All right, so let's let the fun begin. We are now going to find the orthocenter. Find the orthocenter of triangle JKL with those vertices. So let's graph those 3 vertices. So now we have our triangle. Now, if we are going to graph the orthocenter, we have to construct the altitudes of the sides. Find an equation of a line containing the altitude from K to JL. So let's start there. So K, we're going to start here at K and draw a perpendicular line. Now here's the good news. JL, we know, has a slope of 0. Therefore, I have to draw a vertical line from K. Well, that's an easy one. There's my altitude. So my altitude here, I'm going to write down, is x equals -2. Now let's go to another side. Let's construct J to KL. So what do I need to do? Well, the first thing you have to do is find the slope of KL. The slope of KL. Why is that? Because you need to find a perpendicular line to that. So the slope of KL. So I'm going to take my points, K and L, and I'm going to subtract my y values, 6 minus 2, -2 minus 2, which is -4. That gives me a slope of -1. Since I want the perpendicular slope to that, the slope I'm going to use is the opposite reciprocal, which is +1. So the slope I want is 1. I also want a point on that line. Well, since I already know we're going to connect J, I'm going to use the point for J, which is -4, 2. Once again, if you're confused yet, I found the slope of KL. I want the perpendicular slope to that, so I did the opposite reciprocal. Since this right here is going to be my line, I need a point and a slope. Point-slope form. Point, I already have a point, that's J. So I'm going to plug this into point-slope form. I'm going to solve for y. Add 2 to both sides. My equation is y equals x plus 6. So I have to graph the equation y equals x plus 6. So if I did that, I would just put a dot on 6, slope of 1, so what do I need? I need the point of intersection. Now, what does it look like? You have to realize that it might not be exact. It could be like a decimal point off. It looks like it's going to be negative 2, 4. But here's what we do. This is where you use what you know. We don't need the third side because we know it's going to intersect at the same point. So I have a system of equations. The system of equations I have is y equals x plus 6 and x equals negative 2. Because this is easy, because I have x equals negative 2, I'm going to use substitution. Substitution, I'm going to plug it in. Negative 2 plus 6, I'm going to solve the system of equations. That gives me the point of intersection, which is the orthocenter of negative 2, 4. The vocabulary are median, centroid, altitude, and orthocenter of a triangle.